Here we are, 8 chapters into our book, and we are finally going to talk about an actual device in its actual function as a semiconductor device. We have talked about p-n junctions as far as when they are at thermal equilibrium. So we've talked about them when they've been at zero bias, which basically means there is no voltage across the terminals. And when that happens, the conduction and valence energies bend through the depletion region, but the Fermi energy remains the same. And then we looked at the reverse bias situation in which we enhance the depletion region and actually cause the conduction and valence energies to go down further, and also the Fermi energy went down, which caused the barrier for current to flow to be even greater. So now we're going to get talking about forward biasing. So what we're going to do is switch the polarity of the voltage, but of course in doing so, the voltage will now be opposing the built-in voltage rather than enhancing it. So this time the polarity is switched. The depletion region and the electric field inside the depletion region are both smaller, and the Fermi level moves up, which reduces the amount of energy it's going to take to get from the N region to the P region for an electron, or from the P to the N for a hole. So what ends up happening is that when we add a voltage, which reduces the depletion region, then we begin to get electron flow in the conduction band, and we get hole flow in the valence band. So we're just going to look closer at kind of what goes on there and what's going to happen. So, first of all, under forward bias conditions, the depletion region will become narrower and electrons and holes will diffuse across the region as the built-in voltage is approached. What ends up happening is the electrons go from the N side, where there are majority carriers, and they diffuse over to the P side and become excess minority carriers. The same thing happens with the holes. They diffuse into the N region and become excess minority carriers on the N side. This is something known as injection. This is when carriers diffuse from one region to another. There is current that is produced when the minority carriers move across the region into which they've been injected. That's the actual current that's flowing when the diode is forward biased. So what we have is we have a p-n junction in which there are more holes on the P side and more electrons on the N side, but there are minority carriers on each side. And what ends up happening is, with the electric field being such that it is, the positive charge attracts electrons, and the negative charge attracts holes, and they begin to move. The hole current is comprised completely of minority carrier holes. The electron current is comprised completely of minority carrier electrons, and the current in the diode ID is just a combination of both of those. So we're going to look at actually the relationship, the voltage-current relationship, and we're going to go through some assumptions. And the assumptions are just necessary so that we will know that we are all on the same page. And I'm sure that the page that I'm on, you're probably just going to believe me that it's the right one. So the assumptions that we're going to make, first of all, we're going to assume that the junction has abrupt boundaries. We made that assumption before when we were talking about p-n junctions, so that's nothing new. We're going to assume the Maxwell-Boltzmann approximation applies to carrier statistics. We also have been doing this all along, so this is not new. This is something that we've been doing, an assumption we've been using. Low injection and complete ionization conditions, which is also something we've been assuming pretty much all along, whether you knew it or not. And then some assumptions about current. We're going to assume that the total current is constant. It may or may not be, but we're just going to assume that it is. We're going to assume that the electron and hole currents are individual or continuous functions through the p-n structure. And in reality, they're kind of, sort of, but that's close enough for what we're going to do. And then the individual electron and hole currents are also continuous functions through the depletion region. So there's no breaking up of functions since it goes in there. So when we have conditions such as thermal equilibrium, and we've looked at this a little bit, this is a little bit different way of looking at this. When we have a PN junction at thermal equilibrium, we have a low amount of energy on the N side and a higher amount of energy on the P side where the conduction is. And the electrons kind of gather at the point at which they can get to, which is before the built-in voltage and before the depletion region, and then they don't have enough energy to cross to the P side. So they just kind of gather and don't do much. When we apply a voltage that brings energy into the system, so it pushes the Fermi energy up, which pushes the electrons up, and now they really don't require all that much energy to start moving. They basically just require a little, and they'll just go flying over into the P region and beyond. And the holes are also moving in the valence band in the opposite direction. You just can't see them, but the holes are moving in the valence band from P to N, and the electrons are moving from N to P in the conduction band. So now what we're going to do is we're going to look at something known as boundary conditions. And this is going to be a theoretical part again, but we're going to get to the end of the theoretical part, and then when we get there, it won't be such a big deal. So we're going to look at the excess minority carrier concentrations right at the space charge boundaries. And that's going to be something that is important in determining what the current is. So we know that the built-in voltage is a function of carrier concentrations on each side of the junction and the material that it's made out of, which determines the intrinsic number of carriers, and then the thermal voltage, which depends on temperature, pretty much. And if we divide both sides of this equation by the thermal voltage, Vt, and remember that Vt is kT over the charge of an electron, we get Ni squared over Na dA is the exponential function times negative E times the built-in voltage times kT. And since, as we said before, we're going to assume complete ionizations, we can actually apply this to the minority carriers. So what we're going to do, first of all, we're going to assume, like I said, complete ionization, which means that the number this means that the thermal equilibrium concentration of majority carriers electrons in the N region, so this is N sub NO, that's just how many electrons you have in the N region. And that's going to equal the donor concentration because the amount of electrons on the side of the N region is going to be the donor concentration. And the number of electrons on the P side, since they are the minority carriers, is going to be Ni squared over the number of acceptors. So we can get on either side of the junction, we can get the minority carriers and the majority carriers. So we've got that. Then what we're going to do is we're going to take that equation that we just got a minute ago, and we're going to substitute in the values of the thermal equilibrium concentrations of majority and minority carriers into this equation. So we're going to take Ni squared over Na, and then we're going to put Nd on the other side, and then we're going to substitute in the carrier concentrations that we just found. And what this gives us is the minority electron concentration on the P side related to the majority concentration on the N side at thermal equilibrium. So this is good at thermal equilibrium. This isn't good at another time, but it is good at thermal equilibrium. So this is good. What we're going to do is we're now going to take this equation and we're going to apply it to a forward bias junction, because this is telling us the majority and minority concentrations at thermal equilibrium, and we need to know what happens if we apply a forward voltage. So if we apply that, then the energy needed to cross the junction is actually less. It's going to be the built-in voltage minus whatever we apply, because whatever we apply is working against the built-in voltage and making it less of an issue. So we're going to use that. We're going to use the previous equation that we got, and we're going to find the concentration of minority electrons on the p side. So we want to know the number of electrons on the p side, and that's going to equal the equation that we used before times the exponential function, and all we did was substitute VBI minus VA for VBI. That's basically all we did. And then we can split up that exponential, because anytime you have exponentials and you've got addition, you can split them into two exponential functions that are multiplied by each other. So we can split up that equation and we get NNO, and then we have exponential function twice with two slightly different things. But the part that is NNO and then the exponential function of minus E VBI over KT is just NPO that we found previously. So we can substitute that in, and what we get from that is actually the excess minority carrier concentration in the P region, which is what we want. We want the excess minority carrier concentration in the P region under forward bias. So that's what we get from that particular relationship. And stick with me. It won't be that bad when we get done. You just need to know where this stuff comes from. So what we're going to do, first of all, we're going to draw this so we kind of see where this is in relation to the depletion region. So at the depletion region, right at the boundary, which occurs at the edges of the width on either side, the N side and the P side, and we can actually calculate at X sub N the number of a number of holes in the N region, and then at negative X sub P, we can calculate the number of electrons in the hole region. And I guarantee you having all those P sub N and N sub P and NOs and POs is confusing, but it's okay. We'll get past that, and then we won't have to worry about it again. But basically what this is telling us is that at the junction, there is a much higher concentration of minority carriers than there is further out. In fact, it's an exponential function. So what this looks like, if you go out from either direction from the depletion region, you actually get a decreasing of minority carriers, but the minority carriers are kind of jammed up against the side of the depletion region. And that's where you get the electron injection and the hole injection. You get that from the fact that there are minority carriers that are excess and are right up against the depletion region, so they almost get pushed in rather easily. So, all this to say, what good is knowing what the minority carrier concentration is? Why do we even need to know that? Are we going to use that? Well, you might have to use it academically, but we're going to keep moving and see that it's not going to be a terrible thing that we're going to use. What we're going to use this for is because we want to figure out the current eventually. We really want to figure out the current. We can figure out voltage because we apply voltage, but we want to know what the current is in the PN junction. And to get that, we have to look at current density because we've already talked about that. And when we are looking at those minority carriers, what they are diffusing, what they are doing is diffusing across the space charge region. So we have an equation that actually tells us how to figure out what the current density is for diffusing charge carriers. However, we aren't going to do the entire derivation of this because it is long and somewhat tedious, and what I'm going to do is I'm going to tell you the end, but because we've been going along, hopefully you'll see that this actually does kind of relate. We have been looking at, back here, logical equations that tell us the carrier concentrations, the minority carrier concentrations. We really don't have an X dependency on either one of those because we're assuming there is a more or less constant value right at that point. But we're going to take those functions and those are going to figure in to figuring out what the current is. So when we take the derivative of the functions that give us the diffusion current for P and N, what we end up with is this. We end up with current densities for the holes, current density for the electrons, and I'm going to explain what all these things are in a minute, but the only thing you haven't seen before is L sub P and L sub N, and I'll tell you what those are in a second. There is a complete derivation of the text. You can go look at it if you want, but this is what you end up with, and you can certainly see how that relates to what we've just been doing. So the current density related to the holes has one equation. The current density related to the electrons has another one. And then the total current density is just the sum of the two. So when we add them together, we get this kind of big, long mess. But the large values at the front are all constants. This constant in front of the exponential function is one that depends on the thermal equilibrium minority carrier concentrations on both sides, and it depends on the diffusion coefficients and the minority carrier lifetimes, which we can't measure, but we could, but we won't. And this value of LP and LN are just ways of relating the diffusion coefficients and minority carrier lifetimes. So how to relate those is given right below. So that whole part in the square bracket, in the first square bracket, is just a constant, which we can figure out. And we give that a name, actually. We call that the reverse saturation current density. So that is a value that if you know some of the parameters in there, if you know the diffusion coefficient and the minority carrier concentration and the minority carrier lifetime, you can figure out the reverse saturation current density, or sometimes it can just be given. It can be measured and given, and we know what that is. So what that means, though, is that we are going to simplify our equation a little bit, and we get our current density is just the saturation current density times the exponential function times E VA over KT minus 1. And this is moving towards the foundation of the ideal current voltage equation for the PN junction diode, because if we know the cross-sectional area, which oftentimes we do, we can change this to a current equation. And this is the diode current equation that we get when we do pretty much any kind of measuring and creating of diode curves. And the saturation current is often listed, it can be listed in a data sheet, the reverse saturation current, so it's relatively easy to find. And you'll notice that the thermal voltage is actually in the simpler form, that we can just take E over KT, which is 1 over thermal voltage, and we just put that into the equation, and that is known as the ideal IV equation for the PN junction diode. It's a general one, and there's one more thing that gets added just to try to kind of make it applicable to all diodes, because all diodes aren't the same. So what was added is something known as the ideality factor. And the ideality factor goes into the exponential, and it's basically just accounts for different types of minority carrier mechanisms that occur in different materials or individual diodes, depending on how they're made. So that factor is generally between 1 and 2, and we oftentimes just assume that it's 1 for simplicity's sake, but for greater accuracy, we can actually use a value. And just to let you know, when you do your semester project, you will determine the value of eta for a particular set of diode data. So it is actually calculatable if you're given data. So this leads us to the diode current voltage relationships. And this is a plot of the diode equation both in the forward and the reverse direction. And you'll notice that the scales are dramatically different in different sectors of this graph. So in the positive sector where the diode is forward biased, the current is going to be in milliamps. Once we reach this diode voltage of 0.7-ish volts, the current will be in milliamps and will be rather large. But the voltage across the diode will never be that big. In the reverse direction, the negative reverse voltage can actually be quite large until you reach a breakdown point in which it won't work anymore when you reach that breakdown voltage. And the saturation current, which does flow, is really, really small. It's on the order of nanoamps, picoamps, even smaller than that, femtoamps sometimes. So depending on the type of diode, that value is going to be really small, but will always be flowing. As you might gather, because diodes are not linear, the resistance is going to change depending on what is going on in the circuit. As operating conditions change, if the diode is forward biased or reverse biased or partially is not quite forward biased, the resistance is going to be different. The resistance will also be different when considering static or DC signals or AC signals, which change. So both of those can be considered. So two types of resistance we're going to look at. We're going to look at DC resistance, which just uses point values from the voltage current curves, and AC resistance, which gets measured using a tangent line to the curve, which means you have to use a little bit of calculus, not too much, just a little bit. The DC resistance is easy. Wherever the operating point is, and we're going to talk in a minute about how to get that operating point graphically, but whatever that point is, we call it the Q point, which stands for quiescent point, and nobody calls it a quiescent point anymore. Everybody calls it a Q point or an operating point or a bias point. Any one of those, they're all the same. So in looking at the graph, we determine the voltage and the current in the diode, and then the resistance is just those values. And if that resistance value is taken in the linear part of the graph, it's going to be mostly constant in that portion of the graph that's linear. If you go down into the knee of the graph, the resistance is going to be radically different depending on what your values are. The AC resistance is a little more, it's a little different. First of all, we're going to be using the diode equation with eta equal to 1 and take a tangent somewhere on that curve. And we don't really need to know where on the curve it is. We just have already discovered an operating point and have determined the DC voltage and the DC current. And that's what's important. We know what the value of ID is in the DC realm because there always has to be some kind of value there. So then we're going to take the diode equation, and we took eta out because it's equal to 1. And then what we're going to do is we're going to take the derivative with respect to the diode voltage. And when we do that, we get IS over the thermal voltage times the exponential function times VD over VT. And what that equals is actually something we call the conductance. Since that's the slope of the line is actually equal to the conductance, since how well the diode conducts electricity. So what we can do is we can take the thermal voltage and kind of combine equations a little bit. So basically the equation I'm going to put up is exactly the same. All I'm going to do is put the thermal voltage all on the bottom. And when I do that, then what I'm going to do is look back up at that top equation again just for a second, because we had ID equals IS times the exponential VD over VT minus 1. And if we look at that, that actually, we can distribute the saturation current, and then when we do that, we actually have this value right here, which is the same as this one down here. So what we can do is we can actually substitute ID minus IS for that value. And when we do that, we end up getting 1 over VT times ID plus IS, because if we move the IS to the other side, that's what we'll end up getting. So once we do that, we can take IS out because it's so incredibly much smaller than ID. So we get approximately 1 over VT times ID. So we're almost there. All we have to do now to get the resistance is take 1 over the conductance, which is VT over ID, which, if assuming we're at 300K, will be 0.0259 over ID. 26 millivolts-ish will be fine. And that's something that is probably one of the only times you will go find a DC value, which will be the DC current, and determine an AC value from that. But the DC current through the PN junction actually determines the AC resistance when you send a fluctuating symbol or signal through there. The last thing we're going to talk about is how to determine what the operating point is graphically. So we're going to look at a series circuit. We don't talk about circuits much in here, just a little bit. And we can solve for the diode voltage and current if we use the relationship between the circuit and the diode equation. And if you haven't had circuits yet, we're going to talk about Kirchhoff's voltage law for a second. And most of you have at least heard of that. But basically, it just means that the voltages going around the circuit all have to add up to 0. So if we take those values and we get Vs minus IDR minus Vd equals 0, and that means that the diode current is going to equal minus 1 over R times whatever the voltage of the diode is, plus the source voltage over R. So this means there's 2 equations that describe this. We have the series circuit equation, and then we have the diode equation. And if we've got 2 equations and 2 unknowns, you can easily solve it. It's just that in this class, we don't solve it algebraically. We only solve it graphically. So if you solve it algebraically, you won't get as much credit as using a graph. It's one of the few times that that's going to happen. So if we're going to use a graphical method, the first thing we have to have is an accurate diode curve, which in general, that can be obtained. There are devices called curve tracers where you can stick a diode in and you can print out a curve, and they work really well. We have several of them in our department. Or you can experimentally determine what the values are, but of course, if you were going to determine that, you would just go ahead and determine what the voltage was by measuring it. So in general, but you do need a diode curve somehow, however you manage to obtain it. And you can actually mathematically determine it if you want. You can print out a graph of the values if you know the saturation value relatively well. That can be done as well. So we have a curve, and then what we're going to do is we're going to take a linear equation that describes the series circuit, and we plot it on the same graph. So that's the ID equals minus 1 over RVD plus Vs over R. We call that the load line. The y-intercept of that line is Vs over R, so that's going to be the intersection point on the vertical axis, and the slope is going to be minus 1 over R. The intersection point on the horizontal axis is going to be Vs, because that's the maximum voltage that you can get in a circuit that has a source voltage of Vs. So that gives you the line that helps determine where that intersection point is. Now that we have the load line, we find the operating point, and it's right where those two intersect. And what we're going to do with that is we're just going to go over to the vertical axis, and that is the diode current right there, and down to the horizontal axis, and that is the diode voltage. And that's all one has to do to determine the diode current and the diode voltage. And this looks really easy. The problem is that frequently the diode curve has a very, very low resolution because the voltage only goes up to 0.7. And usually your source voltage in the circuit it's like 5 or 10 volts. So often resolution is lost because the diode curve gets crammed into the far right of the graph, and then the current ends up being way up close to the maximum current. So that's one of the issues with using graphical methods, is the resolution is not that good. But because this is not a circuit analysis class, we do not use circuit analysis in this class. We only use the graphical method to find the operating point.